Okay, so in this problem, we will again learn how to use Arrhenius equation to find out the value of A, the frequency factor, and the value of EA, that is the activation energy. And you can see on the screen the famous Arrhenius equation, that is K equal to A into e to the power minus EA by RT. Here the A is the frequency factor and EA is the activation energy. And if we take logarithm or ln of this equation, then we can have an equation like this: ln Ka equal to ln A minus E by RT. And if we plot this thing, right, so in a semi-log plot, you can see that K versus 1 upon T, we have a straight line with a slope minus E by RT, and the intercept should be ln A. So from plotting these things, we have seen this kind of example, knowing the values of K at different temperature. And we plot the Arrhenius plot and find out the value of E and A. And this is the second type of data that you may have. So it is not, the value of K is not directly given. It is given as a rate of reaction. And from the rate of reaction, we need to extract the values of K, right? And then we plot the Arrhenius plot and find out the value of E and A. That part will be very easy. The first trick, if you see, look into the problem now here. So we have an elementary reaction here. So elementary reactions means that the order of the reaction is the stoichiometric coefficient of the species over the concentration terms, right? And if you see the data here, basically this is the initial rate data. So at the beginning, what is the rate of the reaction that we are measuring at different temperatures? So we start, every data is for a new set of reaction at the beginning at temperature 300. At the beginning, what is the rate of reaction? And we fix for this thing, we fix the concentration of A and B. It is an irreversible reaction, so the rate law only involves the concentration of A and the concentration of B. So we fix the concentration of A and concentration of B all through the experiments here. So you can see that at 300 we have some value, and at 360 Kelvin we have some values. But all the experiments results with the concentration of A of 2 molar, that is means 2 moles per dm cube, and B is 1.5 molar, that means that 1.5 mole per dm cube. That is the concentration, initial concentration in A and B in the reaction, and we just measure the rate for things, and we can find out the value of K from the rate expression. Another information, we can see that we know that with the increase of temperature, reaction rate will also increase, right? So we can see also that at 300 we have 0.002, whereas at 360 we have 8.3. It's a huge jump in reaction rate. And what is the reaction rate? Reaction rate is a function of Ka, that is the reaction rate constant, and the concentration of the species that are involved in the reaction. And K, basically the reaction rate constant, is a function of temperature. So when the rate changes with the increase of temperature or with the change of temperature, basically it is the value of K that is changing, right? So we'll try to find out with this data what is the activation energy, what is the frequency factor A, and what is the rate constant K value, that is the rate constant, as a function of temperature using T equal to 300 Kelvin as a base case. So these are the queries they ask here. So first thing is we need to find out the value of K from the rate data, and then we can plot the Arrhenius equation or Arrhenius plot, find out the slope and the intercept, and we have our results, right? So the next slide you can see that it is an elementary reaction, so we can write down the rate law for this reaction as minus Ra equal to Ka Ca square and Cb, right? Concentration of A and a concentration of B. And if we rearrange these things, we can find out the reaction rate constant Ka equal to minus Ra divided by Ca square and Cb, right? So that is how we can use the data to find out the value of K, right? And now we know that Ca value and Cb value are constant for each temperature. The data we are seeing here, this is the initial rate method, right? We will learn that thing in chapter 7, so how we can have these kind of things. And predict the reaction order from the initial rate data, but it is in chapter 7. For this problem, we can see that in Ka can be calculated if you know the value of Ra, Ca and Cb. Definitely, as Ca and Cb are constant and Ra values are provided, we can easily calculate the value of Ka at different temperatures. And once we know that thing, we can make a plot of Arrhenius, we can make an Arrhenius plot like that, right? And that we will do it in Excel. So hopefully you can see the Excel slides here. I have already put the data here, basically the temperature and the rate of the reaction. We have a minus sign here, right, because it is a reactant. You can think A as a limiting reactant if you want. So first of all, we need to find out what is the value of Ka. So we can say that Ka in this column, we can find it out according to this equation, right? According to this equation is minus Ra, so that is this column, divided by, we put a bracket because we have Ca and Cb. So we know that Ca is constant, is a 2 mole per dm cube to the power square, and it's multiplied by Cb is 1.5. These are the fixed values, right? So you can see that the K values we can calculate directly like this, right? So, and also it is written here the Ca value and the Cb value, and the Ka value is directly calculated, right? And we can just copy and paste for the rest of the values of R, Ctrl C, and you can just paste and you'll get all the values of Ka for this reaction at different temperature, right? So now we will try to generate the Arrhenius plot. So that is x-axis is 1 upon T and y-axis is ln of K, and then we make the plot out of it, right? So we will make it 1 divided by T, and that will be equal to, T is our first column, you can see, so 1 divided by our first column. So just enter, so you'll see our value here, then we can just copy and paste the things. Right, so we have all values of 1 upon T, and then we take ln of Ka, right? We have done it in our first example in the video, if hopefully you can see it. So it will be equal to ln of, in bracket of this Ka value column, right? And we have our value. We have a negative sign for that because it is less than 1, right? So okay, we have a very big value here. I can see it here, 360. Let's see. We need to plot it first, and then we can see everything works fine or not. Right. So now again, one thing is what is the unit of Ka? Right. So first, then we need to ask what is the order of the reaction. If you see the reaction, the Ca squared and Cb1, right? The concentration power of the concentration is 2 plus 1. So the order of the reaction, you can see the order of the reaction will be 3. So it is a third order reaction. So the unit of K is equal to, it is, I hope you can remember, it is dmq divided by mole to the power 2 into 1 by S. Okay, so, or divided by S. Right. It's a little bit, I'll show you in the PowerPoint, so it should be like this, something like that, then it will be much easier to understand, right? Yes. Okay, so it looks like this one, so I need to write down nicely to make you understand. So it is a third order, and we know how to write down the unit for the third order reaction. In chapter 3 we learned that. So now our task is to make a plot, Arrhenius plot, right? So we just highlighted the values that we are going to use. So we select the data set, press insert, we'll take the scattered graphical approach and just plot, take the data points, scattered points, right? So this is basically the plot, Arrhenius plot. We can change the position of x and y axis because it is really shifted right from the 0 values, right? So both things we can change So you can see that the axis value here in column bar in the format axis format option. So we check the axis values crosses at like 0.0025. You can say 0.0025. Fine, fantastic. And then we can put a minimum value of 0.025, right? So we can have, and then we can just press the y value is as axis value as -9. That can be the -9. So, and you can see now the plots are now very nice looking. It's just manipulating. If you don't do it, you'll get the same resulting. So this is the Arrhenius plot, right? For example, problem 1. So the problem 1 Arrhenius plot things, and we know that this y-axis is ln k and x-axis is 1 upon t. So if you want, you can make design and add elements, axis title horizontal, that's 1 upon t, and also you can design and axis title and primary vertical axis is ln of k. So you can just write down to look it very nice, right? Oh, it didn't work. Okay, so you can also write down if it does not work in that way. Okay, also, and press enter. Hopefully you can see it. Now we know the rest of the things. We will fit the data sets with a trend line, that is a straight line, and find the slope and intercept from there. Right, so just select it, add trend line. If you right click on your mouse, click on the right button of your mouse, then add trend line, select the linear line, and don't forget to select these two things: display equation on the chart and display the R square value on the chart, right? So you can see it here. We can increase the font size if you want, so you can make it a little bit larger to see it nicely, and also you can have a format to shape the field as white, so we can have a nice view of the data points, right? So you can see the fit line is -14999x and plus 41.995, and we know from our knowledge that the slope is -e by r and the intercept is ln a, right? So the slope equal to, you can say that -e by r, or you can just, if you want to write down e by r, that will become, as I cancel the minus, so it will become a plus sign 14999. So that is our e by r, and the unit of e by r should be Kelvin, the temperature unit, right? And we can calculate our activation energy value, E equal to 14999 multiplied by the R value. R value you can put 8.314. That is basically joule per mole per Kelvin. So you'll have basically the unit as joule per mole. Also, you can divide it, this joule per mole, by 1000. So if you divide it by 1000, it becomes kilojoule per mole unit. Similarly, you can also calculate it for calorie. I have shown you in the previous example. If you forget it, just go and review example 1. And also you can find out the intercept from here. So A will be exp, sorry, I need to press an equal sign, exp, write down exp, then bracket of 41.995, and we have the value of 2 into e to the power 2 into 10 to the power 18. And also, if you can change the format of the cell to get a very accurate number things, right? We can have a scientific with a decimal place up to 0.2. Usually we do it. So you can see actual value is 1.73 into 10 to the power plus 18, and we know that the
the unit of A should be same as the unit of Ka that we are having here. So we should just copy and paste